What is the average throw on a dartboard? If you want to follow along with a decent grasp on what's being shown, this video is made so anybody with a basic knowledge of statistics and calculus can follow. Let's first assume we aren't good at all and we want to maximize our chances. Where would be the best place to throw our dart? Well, this would be in the middle, double bullseye. How do we know this? We can prove this by visualizing a circle. This circle is everywhere we can throw, so the more area we can cover of the dartboard would be better. Let's take a throwing circle with the same radius as the dartboard. The only place where this circle completely overlaps the dartboard is in the center. Now, as I said before, I'm not good at darts, so this circle for me would be large. It's pretty logical to see the radius of the circle would decrease with better skill. Let's see how small a professional circle is. They also typically aim at the triple 20. Now, this would probably not be a circle in actuality, but for the sake of ease, let's assume it is. The actual shape would look something more like a shape with a horizontal symmetry but no vertical symmetry due to the effect of gravity and the way small changes in angles from the starting location would affect the trajectory. As we can see, the best location for bad players would be in the middle. Now that we have a point to aim, let's discuss the probability distribution shape. Let's start off with the easiest distribution, the linear distribution. Or in this 3D case, a planar distribution. This basically means every point inside our circle is just as likely to get hit. Since our base shape is a circle, we'll extrude it and there you go, a cylinder. We need the total volume of the cylinder to be 1. I leave it up to you to figure out why exactly. See it as an exercise to the viewer. We are unable to resize the radius since it's dependent on our player's skill level. That leaves us with one variable, the height. Volume for a cylinder equals pi times r squared times the height. And in this case it is equal to 1. Just reform the formula to calculate the height. Height equals 1 divided by pi r squared and there you go, you have the height. Now for the most important formula of the entire video, the formula for the expected value, or E of x. In the case of our planar distribution, the variable will be the radius, so E of r. All this formula does is take the weighted average of all possible scores. In our case, the score is the points you get of the area you landed in, and the weight is the size of this area. Now I have one more trick up my sleeve. Note how the points all lay around the center, and on any given radius, these amounts have an equal share. We don't have to use every little segment on its own. We can use the area of the ring of equal points and use this score to make our calculations more efficient. This is just a normal average, so 1 plus 2 plus 3 all the way up to 20 divided by 20 and you get 10.5. Now we have 6 sections, or 7 if your circle is so big you throw outside of the dartboard. After a quick search for dartboard dimensions, I came to these dimensions. The different regions have the following scores: 50, 25, 10.5, 31.5, 10.5 again, 21 and 0. Note how the double and triple area is just 10.5 times 3 and times 2. I'm sure you can figure out why. Now we have a bit of a problem. Let's assume our radius is 50. That means we'll hit the double bullseye, and the first singles. We don't hit the doubles, triples, or the second singles. We have to adjust the formula for this problem by setting limits to our function. These limits will be the different regions. Now we can finally build the formula. If we plot this out, we have the following trend. A sharp decline from 6.35 onwards. And these regions where the score gets bigger. Let's try to find a rational explanation for this phenomenon. As you can see, this growth happens twice. Once at the triple region and a second time at the double region. What do both these regions have in common? They increase the score from the previous segment. Because the area you can now hit includes high scoring areas such as 31.5 and 21, you could expect this actually. There isn't really a gradual change, the segments are either inside the circle or they aren't. This is what causes this growth in average score. But this model doesn't seem right. A circle your dart always lands in, even the best players can't guarantee their shots will be perfect every time. And how is it that the edges of the circle are just as likely to get hit as the dead center? We need to find another model. A model that's more realistic. It should have a higher chance in the center and not be so limiting as our circle. So we have the following conditions. The highest chance has to be in the center, it needs to be more realistic, it needs to have a gradual change, and it still needs a defining feature for skill, like the radius in our circle. This lands us on the normal distribution, or the bell curve. Chances are, you've seen it used before, maybe in school. This time we'll use the 3D variant. The formula used for this distribution is the following. You can see it here on screen. That is a big boy. We'll try to do the same as we did with the planar distribution. This, however, isn't the basic shape like our cylinder, so to calculate the volume of this shape we'll have to use a double integral. For those of you who haven't had Calc 3 yet, don't worry. A double integral is just a normal integral, but you use it to calculate the volume in this case. It also allows for some fun tricks. This integral doesn't seem too easy to solve. But let's look at what we actually want. Circles, or rings to be exact. One of the fun tricks is a change of basis. We can switch from xy to r and theta for circular coordinates. For those of you who don't know what these are, take a look at the screen, they're pretty basic. Now you use the following formula, x equals r cos theta and y equals r sin theta. To adjust for distortions, you need to calculate the Jacobian, which is basically the determinant of a matrix differentiated to the different variables. In this case, the Jacobian is extremely nice because it gives us an easy way out of this integral. Split the variables, substitute for minus r squared, and it's basically solved. Evaluate from 0 to positive infinity, and you get pi, or 2 pi sigma squared if you use the adjustable version. Now you just need to divide your base formula with this value. What you see here on screen is the solution for the standard form to set the total volume to 1. You can do the same for the rings. Try it, it's easy once you know how it's done. Get the weight of our rings. Once again, our choice of aiming at the middle helped us out. Before even starting to try calculating a hard-looking integral, try to look at the possible shortcuts. It could make your calculations so much faster and so much easier. With x being the standard deviation, we can plot out our e of x for a normal distribution. Now, I hear you say, that's cool and all, but how do I profit from this? How can I use this to calculate my own average? I made a tool for this in Desmos. Just resize the circle to your skill level and it will give you an average score. I made one both for the planar and normal case. I'm sure you can figure out which one is better. By evaluating the bell curve from 0 to 3 times the standard deviation, we can see that 98.9% of the shots hit this area. So, if you measure this radius where you score the most shots, you can take this radius, divide it by 3 and plug it into the formula. If you want to use the planar distribution, simply don't. Although it's pretty easy to calculate, it's not as accurate, but I won't stop you if you just want an easier exercise. Here you just need to find an adequate radius and plug it into the formula. Let's compare the two distributions to each other. This once again shows that the planar distribution isn't the best distribution for the job, but if we lay these two functions on top of each other, we can see similarities. This is beautiful. It also shows how practice takes a pretty long time until you get better. What I want you to learn from this video is that sometimes hard-looking exercises may look daunting and hard at first, But try to look outside of the box. Maybe you'll find an easy way out. And don't be afraid to fail. Seriously, in mathematics you just try a different approach. If your current approach didn't work, try to look at the shortcomings of this current technique. It may just hide in rotational symmetry. Thank you for watching my participation to the Summer of Math Exposition. I'm trying to figure out what kind of video is best for me to make. I know I haven't made videos in a while. I want to make them, I really do, but being a student, a coach and a private tutor doesn't really help. I covered the explanation of the integral pretty quickly in this video because it wasn't the main point I was trying to make. If you want the full explanation, I'll make another video about that topic, but probably not animated since I'm still trying to figure it out. If you have any questions, I'll gladly answer them in the comments. A special thanks to Desmos for allowing the participants to use their calculator. Have a great day and good luck to the other participants.